So now that we set up the Schrodinger equation for the rigid rotator, let's look at the solution. The Hamiltonian was minus h bar squared over 2I, second derivative with respect to this polar coordinate phi, and psi equal e psi. So let's try to solve that using the methods we already know. I'll just rewrite that equation here. Schrodinger equation, rigid rotator in 2 dimensions. This is second derivative with respect to that angle phi. That's equal to that operates on phi. That's equal to e on psi, e psi. H psi equal e psi. All right, let's rearrange this. Let's multiply both sides by 2I over h bar. It's h bar squared, sorry. So we can get it in the form familiar to us. So this would be second derivative with respect to phi of psi. That's equal to 2IE with a minus sign in front divided by h bar squared psi. Now this is a form which we've seen for particle in a box and so on. We can immediately write down what the solution is. Phi, this will be a function of this angle phi, so it'll be psi of phi. A lot of Greek letters here. That's equal to a e to the minus I. Now we've usually been using k, but let me use m because that's what everybody uses here. I am phi. No, I'm not phi. My name is Professor Dix. I am not phi. Plus b e to the I m phi. And let's combine these to say c e to the plus or minus I m phi. Okay, so that's the solution to the Schrodinger equation because we've already considered this kind of differential, linear, homogeneous, for second order differential equation. All right, now let's put boundary conditions on here, and then because we're putting boundary conditions on this wave, we'll get some sort of quantum behavior coming out. So what boundary conditions do we need? Now, the independent variable here is the angle. So let's actually draw that here. This is the XY system, but we're changed to polar coordinates. And here's our particle, and it's rotating around in a circle here. Around a circle. Okay, there we go. That's the circle. Sound like Bob Ross. Okay, so that's the circle. It's rotating, say, around this way, which means the angular momentum is coming out towards you by the right-hand rule. And this is going to be a wave function, so it's going to go up and down like this, up and down, up and down, up and down. What we want is that when the wave function hits here again, we want it to be the same value as it was when it started. So we want the wave function at some angle phi, and this is the angle phi we're talking about, to be equal to the wave function when we go all the way around the circle. So this would be the angle phi plus 2 pi. We'll be measuring angle in terms of radians. So if you go all the way over to 2 pi, you want the wave function to end where you started from. Otherwise, you won't have that continuous behavior and things will degrade and so on. So there is the quantum or the boundary condition, and we'll see just in a minute how that leads to quantization. All right, well, let's put in this what phi is. So we want c e to the let's incorporate the plus or minus into m. So m we now can say would be positive or negative. So this is e to the I m phi. That's equal to c e to the I m phi plus 2 pi. There's our boundary condition. The wave function has to be continuous right there. All right, so let's cancel out c. E to the I m phi will cancel out. So what we're left with is 1 is equal to e to the I m 2 pi. All right. Let's use the Euler relation. So e to the I m 2 pi is equal to cosine of m 2 pi plus I sine of m 2 pi. All right, so this is a real number over here. And here's the real part, and here's the imaginary part. In order to get the right-hand side, this to be equal to a real number, this has to be equal to 0 in order to get that a real number. So this means that 1 is equal to cosine of m times 2 pi. Now, what does m have to be in order to get this to be equal to 1? Well, clearly m could be 0, and cosine of 0 is 1. Let's say if m is 1, cosine of 2 pi is also 1, but m could also be minus 1 because cosine of minus 2 pi is also 1. So m could be plus or minus 1, there's that plus or minus coming in, plus or minus 2, and so on, all the way up to infinity. So this is a quantum number m, and it can only have certain values, which means this wave function can only have certain values, certain frequencies or certain wavelengths. Now let's see how we can get energy out of this. So remember, this quantity m is related from our discussion of linear homogeneous second-order differential equations. This implies that m is equal to the square root of 2ie over h bar squared. That's what we said. We used to use the term k for that, but now we're using m because that's what the textbooks use. All right, so, and that square root of minus 1 came in this I term here. So we know that, come back here. All right, so we know that m is equal to the square root of 2ie over h bar squared. Or let's square this. M squared is equal to 2 times the moment of inertia times energy over h bar squared, or solving for E has to be equal to h bar squared over 2I, moment of inertia, times m squared, where m is a quantum number, has to be one of these integers up here. So that means energy is quantized, and the quantization is given by these quantum number, and that quantum number came out because we had to apply the boundary condition that the wave function, where it ends up, has to be where it starts from in this circular orbit here. All right, so that's an important equation here. I'll put a box around that. And now we have the wave function, psi, a function of phi, is equal to c e to the I m phi, where m is a quantum number 0, plus or minus 1, plus or minus 2, and so on. Let's find out what this constant c is. That'll be the normalization constant. Okay, so the way we do that is to integrate over all space of psi star psi over all space. Let's apply that to here. All space for this particular system is from 0 just to 2 pi. That will incorporate, in the phi dimension, that will incorporate all space. So that means that the integral here is from 0 to 2 pi, that's all the angular space of the wave function, which is c e to the I m phi. But look at this. We have to take the complex conjugate, and this is the first time where the wave function is actually an imaginary number. So now we're going to take a complex conjugate, so that puts a minus sign there. And then psi will be c e to the I m phi. All right, so let's take out c squared, and this has to equal 1 for normalization. We want to normalize, mean the integral of all probability density times all volume should be equal to 1. So this would be c squared, the integral from 0 to 2 pi of e to the I m phi with a minus sign, e to the I m phi, and we're integrating, by the way, over this independent variable d phi. And c squared, what is this? Well, that looks like that's equal to 1, right? E to the x times e to the minus x is equal to 1. So this is just the integral from 0 to 2 pi of 1 d phi So this is just c squared times 2 pi. Okay, it's a pretty easy system to solve. So 1 is equal to that, so c squared is equal to square root of 1 over 2 pi. C is equal to 1 over the square root of 2 pi. So now finally we have our wave function, which we're using the symbol m as a quantum number, or denoting some particular state, is 1 over the square root of 2 pi e to the I m phi, where m is quantum number 0, plus or minus 1, and so on. Okay? So we go back here. So we got that solution. It wasn't too bad to get that solution. Now let's look at the energy levels and see what they mean. E sub m is m squared h bar squared over 2I. So let's rewrite that. Energy of the mth state is equal to m squared h bar squared over 2I. Okay, so let's look at those energy levels. Let's look at the m equals 0 energy level. When m is equal to 0, the energy is equal to 0. I guess that means when it's not rotating, it has no rotational energy. Let's look at the m equal plus or minus 1. Plus or minus 1, oh, look at that. They'll have the same energy because you're squaring it. So this would be h bar squared over 2I. So two values of the quantum number have that energy. Let's look at m is equal to plus or minus 2. Again, you have two values for that energy. 2 that squared, that'll be 4. So the energy here will be 4 h bar squared over 2I, and so on all the way up to infinity. The energy levels are not equally spaced. They go as a square of the quantum number. Okay, so energy levels are doubly degenerate except for the m equals 0. And then again, for a dimer, we use a reduced mass instead of m. We'll use the reduced mass mu. And m appears in the angular momentum. It's mvr. So now it's mu vr, and I is 2mr squared. Now it's mu r squared. All right, let's go back here. And let's write out what I is. So this is m squared h bar squared over 2mr squared. Note, these chemists really are screwy with their notation. Note that the same symbol here means two different things in the same equation. Up here, that m means quantum number. And this m down here means mass. So don't be confused. Take it in context. This m is quantum number, that m is mass. And then when you're using a dimer, this will be m squared. The confusion goes away when you're using a dimer. H bar squared over 2 mu r squared. Okay, so with that, I think we've pretty much explored what the solutions to the Schrodinger equation for a rigid rotator are. Here they are in summary. Our first wave function with an imaginary number. Well, that's kind of interesting. And also the energy goes as m squared, where m is an integer, not to be confused with mass.